Another simple algebra with logs, okay? So converting back and forth between exponentials and logarithms. However, they are equations as well. They're equations. Just like with the very first example we saw, the log 3, this actually equals y. Y equals log 3 of x. Notice how here there are two variables. One equation, two variables, you actually can't solve it. That's how we got this blue line here, okay? You can graph those without having to graph the exponential. We're going to try to do that now. Okay, you don't have to graph the exponential. You can just use a table of values. Like I said, a table of values will work for absolutely any equation. From linears all the way up to logarithms. You can use it for everything. Okay, so if you forget, was this the one with the slope? Is this the one where I need to find the factors and I need to find the vertex and then I do this and this and that? Is this the one where... No. Use a table of values. Don't panic. Use a table of values. Okay, so example number 1. Graph the following logarithmic function. Log 3 of x, that's how I say that, log 3 of x is equal to y by creating the table of values. Now I don't want you to panic. Sometimes you may see it in the alternative form where y is first. Maybe that comforts you, right? Because y needs to be first. And that's fine, whatever. Some people like log first because they're used to log being first. But again, equal sign, inverse property. Like you can just switch around, like doesn't really matter. Symmetric property, pardon me. Same thing out. Most people like it the way it was typed because of the table of values. But you'll see that in a second. Alright, table of values. Here we go, x and y. Here's the thing though. It's actually going to be easier for me to pick y instead of pick x. Let me show you. Let me show you why that is the case. Haha. If we look at this, right, and we convert it to an exponential. I'm going to choose a different color here. Let's use red. If I convert that to an exponential, I get 3 to the power of y is equal to x. 3 to the power of y is equal to x. Okay? Okay. Not too hard. It's going to be a lot easier for me to just choose exponents than for me to just choose x's. Right? If I choose something like 3 to the second, well, that's easy, 9. But if I choose 3 to the y is equal to 10, now I gotta figure out how to find y. What to the third power is 10? I don't know, 2 point something. Like, that's gonna be hard to figure out. So instead of choosing x's, we're gonna choose y's. Because notice they'll plug in really easily. And it's almost like plotting a backwards exponential. It is plotting a backwards exponential because they're inverses, right? So we're not going to do this. We're going to do this. Alrighty. Well, we've already got 2, so let's just use that one. And maybe we'll use 1, 0, -1, -2. We'll use 5 because it's our first time doing this. I usually only, after like 10 or 20, you start to see the pattern. You could probably narrow it down to 3, 1, 0, -1. But until then, maybe use 5. Get yourself a nice, solid, like, concrete base. Alright, well, we got this one's 9. 3 to the first, that's going to be 3. Oh. My apologies. I hit the button. Don't hit the button. Okay. Okay. 3 to the 0, that's 1. 3 to the negative first, that's going to be 1/3. And 3 to the negative second, that's 1/9. The reason I breezed through those is because we've done them 3 times now. Right? We did those 3, made that table 3 times now. It's just now backwards, right? It's backwards. All right. Because it's backwards, I have to be very careful plotting it. I have to be very careful. I'm going to start with some axes. Never. Okay, hold on. Next time I make these notes, I'm just going to put in ones with axes. Good enough. Okay. So, like I said, I have to be careful now, because I know the tendency is when you switch the table, you want to switch the point as well, right? So I put in 3 squared is 9, so my point is 2, 9, right? But it's not. It's still 9, 2. They still go in the order of the table. So this is still out 4, 8, 9, and up 2. So there's the point. All right, just be very careful of that. Second one was out 3 and up 1. out 0, I'm sorry, out 1 and up 0. Do you see, even I did that. Out 0, up 1, when I meant out 1, up 0. And then out 1/3, up, down 1. Urgh. One of these days, man. Okay, sorry about that. And then 1/3. Okay. Keeps jumping to the top of my notes. I'm really not sure why, to be honest with you. It's fine. Okay. And it goes down like that. Alright, we have our logarithm. Always kind of splits the y-axis. You're going to see later, if you see in the next example, it could be flipped over the x-axis, but it's always going to be kind of on that side. Okay. Sweet, let's do another one. Graph the following logarithmic function. Log, pardon me, 1/2 of x is equal to y. Creating a table of values. Okay, so let's just do it now. X, y. Let's convert this, because as it is, it's a little messy. Let's go around. 1/2 to the y is equal to x. Alright, so our base is a fraction, but that shouldn't scare you. It doesn't. We did those with exponentials, right? It doesn't really change much. Just kind of, a fraction. So we'll do 1, 0, and -1. But notice I picked y, not x, right? I picked the right side, not the left side. In the very few cases where it's easier to find the output than it is the input. Alright, 1/2 to the first, that's just 1/2. 1/2 to the 0, that's 1. Because anything to the 0 is 1, even 1/2. And 1/2 to the -1, if you flip that over, it's going to go back to a whole 2. Alright. Draw me some axes. And input my information. Now again, I have to be careful that I don't accidentally put 1/1/2 in, because that's how I solved it. I want the point 1/2, 1, right? So I'm going to zoom in so I can find 1/2, because that's pretty far down there. 1/2 up 1. Out 1, up, 1/2, 1. Out 1, up nothing. Down 1, no, out 2, down 1. Right? Because that's what I got. Out 2, down 1. And we can see that this is, in fact, a logarithm. Again, if you want to do 5 values, 7 values, 9 values, whatever you want to use so that you think you have enough, that's up to you. I wouldn't choose all positive. 1, 2, 3, 4, 5, 6, 7 is great. But you're only going to see 1/2 of the information, right? You want some negative numbers. I know nobody likes to deal with the negative exponent rule, but you have to. You've got to do the other side. You need to do the other side or you're going to mess it up. Okay, and there's a beautiful logarithmic equation. Well, let's do another one. Graph the following logarithm. See if you can try this one by yourself. It's not complex. There's no fraction here. So try it out, then come back. Okay, hopefully you tried it out. If you didn't, please pause the video and then come back. But hopefully you tried it out. So I'm going to convert this. 5y equals x, right, around in a circle. Make a table. Choose my y's. 1, 0, -1. 5 to the first is 5. 5 to the 0 is 1. 5 to the -1 is 1/5. Very similar to the log 3 problem, right? Okay. We had 5 to the first is 5, so out 5, up 1. Out 0, up nothing, or I'm sorry, out 1, up nothing. And down 1 and out 1/5. That should be a lot closer. Like there. Okay, cool. And now connect the dots. Okay, now I'm not just going to go, in fact, I really shouldn't have connected it that way because 5 to the second is 25, and that's going to be way off my graph, right? So I want to be really careful that that bar, this line here, doesn't just randomly go up, right? It doesn't hit 2 until 25x is out. So I kind of have to draw it skimmed like that. And then I also, on the other hand, want to be careful of the asymptote for the logarithm. Yes, there's an asymptote for the logarithm. Just like y equals 0 was an asymptote for an exponential. Recall that up here, right? So we were up here, and we were graphing exponentials, and we had this asymptote thing where it leveled out. We now have the same thing down here with the logarithm, but this time it's going along the y-axis. So this is the asymptote. I think I'm actually in this problem, yeah. So this is the asymptote. Oop, maybe I shouldn't draw it in the next problem. Let's go like that. And this time, it's x equals 0. Once again, you're like, Ms. K, that's the y-axis. But no, I agree with you. It's the y-axis. I'm not disagreeing that that's a statement. But this is the line where x equals 0. 0, 0, 0, negative 5, 0, negative 10, right? It's always x equals 0. So the asymptote is x equals 0. All right. I think that's okay. That's okay. All right, so example number 4, graph the logarithm function 1/3. Same thing, but let's get another try just in case, because you're watching this video for some reason. Either you were absent or you need a little bit more time with it. So we're going to do another one. Just going to keep practicing, right? So I take the log, convert it around. 1/3 y is equal to x. Now I create my table, x and y. I'm going to choose the x's. I'm not going to choose the x's. I'm going to choose the y's because it's going to be easier, right? It's an exponent, so I'm going to choose the y values. I'm not going to choose the x's. 1, 0, and negative 1, right? All right, 1/3 to the first. What I'm doing is I'm plugging in now. So 1/3 to the first, well, that's just 1/3. 1/3 to the 0, anything to the 0 power is 1. So that one's nice and easy. And then 1/3 to the negative 1, well, that flips it over, right? So 3/1, or just 3. So I have my 3 points now. All right, I'll head over here. Gotta be careful, don't plot them backwards. You're not plotting an exponential. You're not just rewriting this so it's an exponential. You're rewriting this so that it's a easier to compute logarithm, okay? So let's draw ourselves some axes. No. Okay. My first point was 1/3 1, so I have to go here, go out 1/3 and up 1. Second point was 1, 0, and the last one was 3, negative 1. And I noticed the little curve. So for me, when I'm doing these, I see just the 3 little curve, and I know that it runs along that y-axis because that's the asymptote, right? And we'll talk about transformation. We'll talk about when that's not the case later. But for now, these first ones, that's always going to be the case. It's always going to run along this y-axis. So you can just go ahead and draw that in. Try and make it straighter than I did. And then on this other side, well, this one is going to actually hit, what is 3 squared? Or what is 1/3 to the negative 2? Well, 1/3, pardon me. Let's go negative 2. 1/3 to the negative 2. Well, that flips it over and you get 3 squared. That's going to be 9. So in this case, it's actually going to hit on the graph before it heads off, right? It's going to be 3, 6, 9, down 2. Again, if you need to see a few more points before you go and draw your graph, that's totally fine. Totally fine. I know it's not going to hit again because the next one would be 27, right? 3, 9, 27, 81. So keep using the table. If you need to use a calculator, I mean, it's fine. Hopefully you know that 3 squared is 9, but that's just saying. But yeah, make sure you've got enough points to make like a coherent image. All right, so that's graphing the logarithms. Let's do one more. Graph the logarithmic function log 5 of x is equal to y, and exponential y equals 5 to the x on the same graph. Well, what do we know about these two? What have we been talking about the whole time? They are inverses of each other. They may not look like it. You're like, I still don't understand how you think these are the same, but backwards. Like, I don't understand. Well, let's rewrite this one. 5 to the y equals x versus y to the 5 equals, or y to the 5x, y equals 5 to the x. Let's just even write this backwards and make it a dramatically obvious point. So I'm just going to reverse the order here. Look at that. What do you do for an inverse? You switch the x and the y. What did we just do? We switched the x and the y, right? They are, in fact, the same. But let's take a look at that visually on the graph. So let's make this table first. No, let's make this table first. Let's make the exponential table first. We're going to choose our x's, right? Just like we would any other graph. 1, 0, negative 1. So I'm not looking at this side right now. I'm just going to kind of go over like this. 5 to the first, that's 5. 5 to the 0, that's 1. 5 to the negative first, that's 1/5. Cool. Let's go ahead and graph that. Okay, so 5 to the first, so I chose the x's this time, right? So I have 1, 5, 0, 1, so out 1, up 5, 0, 1, and back 1/5. Okay, so I have this exponential. And I was careful. That is the order with which it appears, right? 1, 5, 0, 1, negative 1, 1/5. This isn't a logarithm yet. We're doing the exponential first. All right, now in a different color, we will do this one. So this one is blue. We're going to choose our y's now instead of our x's. So I'm going to choose 1, 0, negative 1. 5 to the first, that's 5. 5 to the 0, that's 1. 5 to the negative 1, that's 1/5. This is sounding awfully familiar. Awfully familiar. Look at those two. It's exactly an inverse. Exactly the inverse. We flipped it around. Remember, when you reflect over y equals x, you change the x and the y. You switch their places. Way back at the beginning, we had 4, 5. It became 5, 4. This is what we are doing with every single point. So it makes sense, right? It makes sense that these two are inverses. Visually, we can see that as well. So let's graph our 3 points here. We had 5, 1, 1, 0. So out 5, down 1. Out 1, no, I'm sorry, out 5, up 1. Pardon me. That's not 5. 1, 2, 3, 4, 5. Out 1, and then 1/5, right? So, and then this skims the y-axis because that's the asymptote there. And this isn't going to hit 2 until 25, which is off the screen. And are they, in fact, flipped over? They are, right? We see this y equals x line in the middle here. And it does look like someone took that red line, flipped it over, and got that blue line. So they are, in fact, the same situation. They are inverses, pardon me. They are inverses of each other. And we've proved it, both geometrically, on the graph, or algebraically, in numbers. Awesome. All right, let's do one more example. We're going to do one from the real world, and then we'll call it a day. Okay. So, in order to change the electrical properties, semiconductors are heated in a process called furnace annealing. Annealing? Sure. Some engineers have to tell me how to pronounce that. The pH of an acid bath used to treat a semiconductor after it emerges from the furnace is supposed to be 3.5. However, the pH can cover a range from 3.45 to 3.55 without the semiconductor being rejected. The pH is given by the formula pH is equal to negative log 10 of C, where C is the concentration of the acid bath. Find the range of the concentrations of the acid bath within the semiconductor treatment is acceptable. Okay, so 3.5 is idealistic, right? But they're okay for 3.45 and 3.55. So that's what the pH can be. So we have two things we need to figure out here. One for 3.45 and one for 3.55. All right. I'm gonna zoom in. Okay. So 3.45 is equal to negative log 10c. And we need to solve for c, right? Okay, so let's solve for c. But let's start by getting rid of anything that's not really vital right now. Negative log. I know you're probably thinking to yourself, what the heck is a negative log? What are you talking about? No. It's the same as negative x. It's negative 1 times log. So let's just divide by negative 1 to both sides. So we have negative 3.45 is equal to log 10c, right? So we'll make our little circle. 10 to the negative 3.45 is equal to c. Now, I don't know about you, but I can't do that in my head. So I'm going to go ahead and grab my trusty dandy calculator. 10 to the negative 3.45. That gave me something that looks like this. 3.54813 dot e to the negative 4. What? Please don't write that on a test. What that means is it's scientific notation. So this converts it, that decimal place is going backwards, negative 4. So here's 1, boop, 2, 3, 4. 0.003, wait, 1, 2, 3, nope, one more, 3, 5. And we'll go 5. So that's what the concentration needs to be. Cool. Let's do the other one now. 3.5, wait, up here. 3.55 is equal to negative log 10 of c. So we'll go around in a circle, right? We go this way, technically. 10 to the negative 3.55 equals, my apologies, I skipped a step. Divide by negative 1. So we get negative 3.55 equals log 10c. If it helps you to visualize the circle, you can rewrite it so that the numbers on the other side, remember the answer to a log, the other side of the log is the exponent. So now we'll make our circle. 10 to the negative 3.55 is equal to c. Handy candy calculator. And I got a similar scenario where I had 2.8183 e, oops, to the negative 4th, which means that decimal place is going back 4 places. So I'll just throw in a bunch of zeros. 28183. Currently it's right here. It's going back 1, 2, 3, 4. So it's 0.0002818. Those are the concentrations between here and here. That is what that is the solution bath can be without the semiconductor being rejected. And that would be the range, I believe. Yeah, it just says range. Okay. And that's what we have as an answer. So sometimes we can see that if we have a log in our equation, we can just convert it and get back to solving for that situation. Cool. All right, that was 10.2. Introduction to logarithms as inverses. Next couple sections are going to be more about logs, things they can do. If you're kind of looking down, kind of glancing ahead, you can see there's a bunch of different rules of logs. But the main idea with this chapter is that a logarithm is an exponential's inverse and vice versa. And those two go really hand in hand. You can use one to find the other. And they're all just centered around that idea of inverses. All right. See you later. No, that sets it for logarithmic rules, okay? But we're going to talk about one more thing in this chapter. We're going to talk about a little bit more about their graphs and how they transform, just because they kind of go along with the rules and what they do. So, I'm going to switch colors here. Once again, I do apologize about my sort of mix-up here. What I've scratched out here, it says in example 1, come on, work with me. There we go. So in example 1, we're just going to draw the graph. Draw the graph of, what was it? Y equals log 5x. Y equals log 5 of x. Alright, so remember back from the last section, logarithmic functions are inverses of exponentials. So it's going to be easier to graph this as an exponential than it is as a logarithm. So let's go ahead and We'll have to circle backwards, but we'll make our circle. 5 to the y equals x. So we'll make our little table. Choose 1, 0, and -1. Remember, I'm choosing y, not x, because y is going to be easier to plug into. There's no legal rule that says you have to choose x. 90% of the time it's easier to choose x. In this case, it's not. So why don't we just choose y? Let's just choose y. 5 to the first would be 5. 5 to the 0 would be 1. And 5 to the x would be, whoops. What would it be? 1/5. Okay, I have 3 points now. 5, 1, 1, 0, and 1/5, -1. So I'm going to draw myself some axes. Okay, cool. Next up, I'm going to plot these points. Out 1, 2, 3, 4, 5, up 1. Out 1, up nothing. And out up 1/5, and then down. Okay, now I know the second one goes up to 25, so I'm just going to kind of keep it within there. And then I also know the asymptote of this is the y-axis. It's not going to cross over the y-axis. It's going to get really, really close to the y-axis. So I'm kind of just going to skim along that. And we've graphed y equals log 5 of x. Why did we do that? I'll talk about that in just a sec. But that was kind of a review of how to draw the log of draw a logarithmic graph. This is what we call a parent function or a parent equation. In this case, it is a function, so we're going to call it a parent function, which just means exactly what you think it means. It's the older brother. It's the original, right? If when you transform it, though, you don't really call them children functions, but that's essentially what they are. You get more of like you get a different graph, but it's clearly similar or made from the first graph. Okay, so parent function is usually the ones that don't have any crazy things going on with x. Okay, we don't see x plus 5, we don't see x minus 2, we don't see a coefficient in front, you don't see anything like that. So the log 3 of x, log 4 of x, log 5 of x, even log 1/2 of x, log 1/6 of x, the base doesn't really matter. It's where the parent function just doesn't have anything on the outside. It doesn't have a coefficient and doesn't have anything happening to x. So these are our parent functions. But we can change that. We can definitely change that. Let's take a look down here. Some transformations. If it doesn't have a transformation, it's just called a parent function. That's what this is, right? But we can do all sorts of things. We're going to focus on 4 main ones. If you throw on an additional letter, an additional number, if instead of just of x, you have x plus k, as it's shown here, what that's going to do is it's going to shift it 1 to the left. Similarly, if you have x minus something, it's going to shift it to the right. Now you got to be careful with that one, because you would think the left side's negative. So if I subtract, I'm going to go to the left, but that's not true. If you add it, it pushes all the numbers back. Okay, I know that sounds really weird, but that's exactly what it does. It pushes everything back as opposed to pulling it to the left. So plus is left, minus is right. If they are not part of the argument, if they're just tacked on the end, so it's not log a of this x plus 2, it's just log x, and then also adding another number like plus 2, then what's going to do is it's going to move up and down. You may recall that back from secondary 1. It happens with everything. So these are the same 4 transformations no matter what. If it's inside the parentheses, you're going left and right. If it's outside the parentheses, you're going to go up or down. Okay, so let's take a look at these. We're going to take a look at one of each, and then we'll be done with the rules of exponents. Okay, I'm sorry, the rules of logarithms. Okay, so we're going to draw ourselves some axes. Okay, now I'm going to spend a little more time on this first one than I am the other 3, because there's a really fast way to graph these, and there's ways to really see why this is a transformation of a parent function. Okay, so we're going to start by graphing this just as it's given. Okay, so we're going to pretend we're just sitting there, right? It's a graph. We're just going to do the same thing we did for all the other ones. So first we have y equals, we have this, so we're going to make our loop. We're going to go this way. We have 3 to the y equals x minus 5. Right? That's our function, right? That's our transformation. That's how we converted it to an exponential. So let's make our table. We have x and y. We're again going to choose the y's because that's going to be a lot easier than try and choose the x's and finding the exponents, right? It's hard to find exponents. So we're going to use the exponents. We're going to choose 1, 0, 1. Or negative 1. I'm even going to choose negative 2 and 2 as well because I want to really see what this looks like. Alright, so I plug in 1, I get 3 to the first equals x minus 5. 3 to the first equals x minus 5. Well, 3 to the first is just 3. So what minus 5 would be equal to 3? That would be 8. Alright, next up we plug in 0. 1 is our answer on that side. Add 5 to it, you get 6. See that? You get 6. Negative 1, you plug in negative 1, you get 1/3. This one's a little harder. X minus 5. We're going to add 5 to that. We get, let's see, 16/3. So x is equal to 16/3. You don't trust me, use a calculator. Plug that in. Plug in x to the second, we get 1/9. I'm sorry, negative 2. X minus 5. Add that to the other side. 5 would be 45/9, so this would be 46/9. And then 2, positive 2, that's nice and easy. You get 9, so x must be 16, right? We add 5 to the other side. I'm sorry, 14. You're going to get 14. 14, so that's that one. Okay, so we have our 5 points now. Let's go ahead and graph that, right? We have 8, comma 1. So 1, 2, 3, 4, 5, 6, 7, 8, up 1, 0, 6, 0, 1, 2, 3, 4, 5, 6, and then negative, it would be 16/3. What's that? 16/3, 15/3 is 5, so 5.33333, right? So 5.33333 down 1, and then 46/9 would be 5.11111. That's like right there. And then we have 14, which is going off the page. So, looks like our function's looking kind of like that. Alright. Doable. Definitely okay. We can figure it out. It's a lot of math, right? We have to solve a little mini equation every single time. But we can do it. The second way to do this is to really treat it as a transformation. Why is this a transformation? Well, let's look at the parent function. Let's look at y log 3 of just x. Okay, so this is the parent function. Log 3 of just x. Okay, just x. If we do that, well, then we end up with, here's my x and y, right? 1, 0, negative 1, 3, 1, and 1/3. If you don't trust me, go back and look at the other videos. We've done this one probably twice now. We're going to plot that on the same graph. Let's see. We had 3, 1, 0 there, and then it went down like that, right? Next one was 9, and then I think the next one's 27, so it went like that. And then, of course, it kind of skims the y-axis. All right, so that's our parent function. Compare those two. How is the pink one related to the red one? Looking specifically here, let's track it. Let's track that. So if I look right here, then from 1 to 6, how far over did that go? That went right. That went to the right. To the right 5 spaces. That's exactly what it did. It went right 5. That's what it did. From the parent function, from the original, from the beginning, it went right 5. And if we look here, isn't that what it said it would do? Right? Isn't that what the table said? When you subtract a number, you go right that many. Here we're subtracting 5, so it went 5 to the right. So what I could do, instead of having to do all these little mini equations, instead I could just plot the parent function, maybe in one color, and then I could pick a few dots that make sense to me, and maybe the ones I chose for my graph, right? And just move them all over 5. That's going to be so much easier and so much quicker than trying to do this little mini equation every single time. And maybe, as long as I indicate to my teacher or whoever's grading my paper, this one, I mean this one, that's right 5. Like, maybe erase the parent function afterwards. But that's all you have to do. It's a transformation 5 to the right. Cool. All right, like I said, I'm going to spend more time on that one than any other ones. Let's just use these other ones and let's just graph these other ones using their parent functions, okay? So what is the parent function here? The parent function would be not y equals log 4 of x plus 2, but just y equals log 4 of x, right? So we're just going to use the basic, the original. So let's just graph y equals log 4 of x to start with, okay? So we have our x and our y. We choose 1, 0, negative 1. Again, you can technically choose whatever you want, but you got to choose both sides, or you're not going to choose both. You're not going to get both. All right, log 4. Let's see. Convert this. You get, I'm sorry, this way. 4y equals x, so 4 to the first equals 4, 4 to the 0 equals 1, 4 to the negative first equals 1/4. Cool, I have enough information to graph this now. Oops. Oh, crud. Okay, good enough. That was much better. Okay, so I have 4, 1, 0, 1, 0, and then 1/4. And then the next one would be 16, so it goes off the page. Again, sorry about that. Okay. And skims the y-axis. The parent functions will always skim the y-axis. Always skim the y-axis because they're parent functions. Nothing weird is happening to them, right? Okay, cool. That's the parent function. Now, according to this, how is ours different? What transformation has been applied here? Let's see. Plus 2, that means it's going to be pushed backwards 2. So it's going to go left 2, right? It's going to go left 2. That's what that says. So when you add a number inside the parentheses, you're going to go backwards. So I'm going to choose a different color. Maybe green, and then these points that we made, I'm going to go back 2 from them. So rather than being on 4, 1, I'm going to be on 2, 1. Rather than being on 0, 1, I'm going to be, or 1, 0, pardon me, I'm going to be on negative 1, 0. Rather than being 1/4, I'm going to be over here. Right, so I'm going back 2. And then we connect the dots. 16 going back to would be 12, so that's still off the page. I'm sorry, it would be 14. So let's go back there, kind of skim there. And then we're going to skim on negative 2 as opposed to on the y-axis where x is 0. And we did it. You're like, Miss K, that doesn't look like everything went back 2. I know. Sometimes that overlap, you kind of think, well, did I do that right? Is it really back 2? I mean, some places don't look the same. But if you analyze it dot by dot, you're going to find that a lot of them, that they are all back 2. Yeah. Okay, cool. Let's try one that is not a left or right. What's happening in this one? Well, notice it's outside the parentheses. It's actually saying do this and then add 6 to it, which is exactly what we're going to do, right? We're going to plot the parent function, log 2x, and then we're going to add 6. It's going to be super easy. So I'm going to use this space here. X and y. The parent function is just log 2x, or 2 to the y equals x, so I'm going to choose 1, 0, and negative 1. That would be 2, 1, and 1/2, right? 2 to the first is 2, 2 to the 0 is 1, and 2 to the negative 1 is 1/2. Alrighty, and I'm going to plot myself some axes. Good enough? Okay. 2, 1 was the first point, 1, 0, 1/2. Now this one I actually might be able to squeeze in a couple more, because if I go by my squares, it's going to be, there's a lot going to be on here, like 2 squared is 4. That's 2, here's 4. 2 to the third is 8, 4 more. And then we've got 2 to the 4th, which is 16, and that's off the page. So I can fit a lot more dots in here. Do you need to put all these in here? No. But your arc should go up to about the 4th one, right? It goes all the way to 4 before it goes off the page. If you just go like this, and that's kind of just lazy. So you don't want to do that. Plus, if you're trying to plot points and move them over or up and down, you're going to get the wrong picture, right? So maybe plot a few more if you know it's like really small, right? Or just always check squared. I don't know. Do whichever you want, but make sure it looks fairly accurate. Accuracy is good. Okay. Now, what is it telling me this transformation is? We kind of already talked about that. It tells me do the parent function and then go up 6, right? Add 6 to each of these points in the vertical direction. If it was minus 6, we'd be going down 6, but it's not. It's add 6, so we're going to go up 6. So from here, it's a good place to start. 1, 2, 3, 4, 5, 6, up. From here, 1, 2, 3, 4, 5, 6. From here, 1, 2, 3, 4, 5, 6. Here, 1, 2, 3, 4, 5, 6. And notice, actually I'm going to use a different color because this is not the same line. We get this, the same kind of curve, the exact same kind of curve, the same speed at which it grows, and the same asymptote here, but it is now 6 up. That's all that's happened, right? Alright, cool. Last but not least, we're going to apply multiple transformations. So what does this one say? Well, it's hard to read because I wrote over it. Boop, there we go. It says, take the parent function and do what? Well, what's the parent function? The parent function, is it log 2x minus 3, and then I have to add 4 to it? Is it log 2x plus 4, and then I subtract 3? It's both. It's neither, actually. It's just log 2x. It's always a parent function, no matter what you do with it. It's the ones that's weird, or that's basic. It's not weird in any way. There's no minus 3, no plus 4. So the parent function here is just log 2x, and if you want, you can put the y on the other side, right? Because then it's easy to draw your circle. So there's log 2x, that's it. So we have 2 to the y equals x. Well, that's super easy. We just did that one, right? So we can do the same xy. Again, it's easier to choose y, not x. So I'm going to choose y. And I end up getting 2, 1, and 1/2, just like we did a moment ago. I'm going to go ahead and plot those. First I need axes, and I'm going to draw a heck of a better line than that. And then this way. There we go. Okay. So I have 2, 1, 1, 0, and 1/2. And then as we saw before, I can also do 4, 2, and then 1, 2, 3, 4, and then 8, 3, and I have my parent function. I wouldn't worry too much about the halves. It's all going to skim the y-axis anyway, so that's fine. But if for the side there, the positive versions, you do kind of want to be accurate. Alright, now, do I have to draw 2 more? Do I need to draw 1 for each? Not really. If I look at what transformation is being happened here, I can apply all of them at the same time. Okay, I only care about the end goal here. The parent function just lets me see where I'm starting. If you want to make sure you're super accurate, yeah, you could do minus 3. To the right 3, right? Because a minus 3 in the parenthesis means right 3. And then you could go up 4. But why don't you just do both at the same time? Why don't I just move every dot 3 to the right and up 4, like counting slope? It's really not that hard, right? So let's choose a different color. Let's do purple. We're going to take this dot and move it 1, 2, 3, up 1, 2, 3, 4. That's where that one went. 1, 2, 3, up 1, 2, 3, 4. That's where that one went. 1, 2, 3, and up 1, 2, 3, 4. That's where that one went. Another thing, if you want to save some time, you can say, okay, well this one's right there, and this is supposed to be one diagonal from it. I'll just go one diagonal here too, right? That's legal. The movement of the curve should not change the curve. Like if you look back at our last problem, like we said, we get the same curve. It's just 6 inches higher, right? So if you wanted to do it that way, you can. You just have to be much more careful about how you move your dots, right? About how you connect your dots. So this one goes over 1, 2, 3, up 1, 2, 3, 4. And then this is going to be, that was this one, so 1, 2, 3, up 1, 2, 3, 4. For example, this last dot I just drew, right? Just because it's moving over 3 and up 4 doesn't mean it's suddenly going to be on one of those vertical lines, right? It's currently sitting at a halfway point. Moving it 3 over is going to move it to 3.5, right? Not 4. So I got to be accurate about this. I have to make sure if I'm moving the half point over, it's got to stay half over. And then we go down. So this y-axis, this asymptote's changed, right? It's moved 3 over. The whole asymptote itself has moved 3 over. And there is my actual function. So this is my transformed function. Maybe I draw an arrow to it. Maybe I grab my pencil and I erase the parent function to indicate that this was in fact the one that I wanted. I wouldn't erase the work. Okay, I wouldn't erase anything we did over here because just in case you make a mistake, Miss K, on the test, I can, give you a few partial credit points, but maybe if you wanted to erase it or grab some colored pencils, you guys know I have colored pencils in my room, you can more than welcome to color it and say, it's the purple one. Okay, cool. Alright, so we've talked a lot today. Talked a lot about rules of logarithms, right? There's the 3 big ones, the product rule, the quotient rule, and the power rule. How they can be used to solve equations, and then how you can graph transformations using these shifts. Awesome. The next section, 10.4, will close out the chapter. It's about common logs and natural logs. You guys are going to love it. It's all about calculators, but at the end of the day, a logarithm is just an inverse of an exponential function. See ya.